Hi everyone, this is the second part of the discussion on absolute value function. In fact, towards the end of the first part, we were discussing about the properties of modulus function and we have a few more properties to go through. So let's get started. Here in this second part, I'm going to begin with this one very important property which is like this. It says modulus of x whole squared is equal to x squared. And let's see how we can prove it. So here we are going to take a couple of cases. Let's say case 1. And let's assume that x is non-negative. So if x is non-negative, how is our left hand side going to look like? Well, left hand side has modulus of x whole squared. So if we remove the modulus sign, x will come out as positive x, and then we have the square sign there. So this is nothing but x squared. And what about our right hand side? Well, right hand side already has, and that is exactly same as the right hand side, as you can see up there. So I'm simply writing it here that this again equals the right hand side. So we have been able to show that the left hand side and the right hand side, they are equal. That means this result, that modulus of x whole squared is equal to x squared, it is true so far, right? Now let's take the second case where x is negative. So if x is negative, then how is the left hand side going to look like? So here the left hand side would be equal to modulus of x whole squared, and we can write it as, because x is negative, it is going to come out as a negative x. That's based on the definition of the modulus function. And then we have the square here. So again, this is negative x whole squared, that is going to be positive x squared. And that is again, we can see that it is same as the right hand side. So here again, we have been able to prove that the left hand side is equal to the right hand side. So for all possible values of x, we have been able to prove that the left hand side is equal to the right hand side. So this is then definitely true. So I'm going to put a double tick mark here that this property seems to be true, right? We have been able to prove it. Now sometimes with this property also, you might see that some authors might say that, hey, we have also this one other property. Let me change the color here. So I'm going to use the green color. So sometimes you might see that, hey, square root of x squared is equal to modulus of x. Well, that is not directly related to this property. However, I can quickly talk about it. And in fact, I have created a completely separate video on a few misconceptions like this, and you can watch that video to clarify your doubt on this particular result. I will provide the link in the description. Now here, if you simply think about just the square root of x squared, and let's see what this value going to be, right? Let's forget that it is going to be modulus of x. Let's pretend that we don't even know that it should be modulus of x. So somebody has said, hey, can you tell me what is the value of square root of x squared? Well, in that case, you have to understand that we are talking about the principal square root. So square root of x squared is actually, this is a principal square root. So this is a principal square root value. And because it is a principal square root, its value should be of the same sign as the quantity that we have within the square root. Now, what is the sign of that quantity? Well, it is a positive sign, definitely, because you use any real number for x, it will give you a positive quantity there. X squared will be a positive quantity, right? So then whatever is the value of this square root, that also should be a positive value. So we are now tempted to say that, well, then this must be equal to x, because we are saying that it's a positive value, right? Principal square root, it is a positive value, so it has to be like positive x. Well, here we have a catch. The catch is that we do not know whether x is actually a positive or negative number, right? All we know is that the square root of x squared must be a positive value. However, how are we going to denote that in terms of x when we don't even know the sign of x? And because we do not know the sign of x, we enclose that within the modulus function sign to always guarantee that square root of x squared will always be a positive number. And I have explained the same concept in my other video also. Feel free to watch that video. But the concept here is that square root of x squared must be a positive value, and this is how we can always guarantee that the value will be positive. When x is a variable and it is an unknown variable, we really do not know whether x can have a positive value or a negative value. But because the square root of x squared must be a positive value, we have to enclose that within the absolute value function or the modulus function. I hope that makes sense. Now let's talk about the next important property here. The next property says that the modulus of x is equal to modulus of x. Here, as you can see, that we have one extra modulus sign on on the left hand side, we already have a modulus of x, which is right here. So this is a modulus of x, and that is again enclosed within another pair of modulus signs, right? So here the property says that you really don't have to put a modulus function value within another modulus sign to make it positive, because just one modulus sign is enough to convert it into a positive number. So here again, let's take a couple of cases. Let's say x is non-negative. So what would be the left hand side? The left hand side is kind of like this, modulus of x. Now because x is a non-negative number, the inner modulus will give us this value. So the inner modulus will give us a positive x, because x is a non-negative number. And here again, this remaining modulus or the outer modulus sign, right, this is again going to give us a positive x. And how about the right hand side? Well, the right hand side has modulus of x, and in this case x is non-negative, so this is also going to give us a positive x. So you can see that both the left hand side and the right hand side, they are equal, and that's exactly what we wanted to prove, right? But this is just the first case. Let's take the second case when x is a negative number. Now in this case, what would be the left hand side? Because x is a negative number, the inner modulus is going to give us a negative of x. And in the previous video, which was the part 1, there we have already proved that modulus of negative x is equal to modulus of x. And again, here you see this is looking like the right hand side. So here also we have proved that the left hand side and the right hand side, they are equal. Now if you want me to show it again, so here we can do like this maybe. Here you can think of it like this. So let me add a few more steps right here as a continuation of this step, right? So here we can say, okay, then because x is a negative number, what is negative of x? Well, negative of x is actually a positive number then. And if it is a positive number, it is going to come out exactly like how it is within the modulus sign. Because x is a negative number, negative x is a positive number. So because we have a positive number within the modulus sign, it is going to come out of the modulus sign exactly like that. And that is equal to negative x. Now, if you think about the right hand side, so let me write down the right hand side. We have modulus of x, and in this case, x is a negative number, so it will come out as negative x. So here again, you can clearly see that the left hand side and the right hand side, they both look equal. So finally, we can say, well, in case 2 also, we have LHS is equal to RHS. So in both the cases, we have been able to prove that yes, that property which is up there that says modulus of mod of x is equal to modulus of x, that property is holding true for any values of x, whether x is a positive or negative or 0. In every case, the property is holding true. So that means it must be true. So I'm going to put a double tick mark here that yes, this is true. We have been able to prove that that is true. Next, we are going to talk about another important property, which is like this. It says that if modulus of x is equal to modulus of y, that would imply that x must be equal to plus or minus y. And let's see how we can prove it. Well, to prove this thing, again we have to consider all 4 possible combinations of x and y's sign, whether both of them are positive or both of them are negative, or one of them positive, another one negative. So let's take all those cases and see if we can prove it. So let's take the first case. Case 1, here let's assume that they all are non-negative. So x is greater than or equal to 0 and y is also greater than or equal to 0. So this is the non-negative case for both the numbers, right? So then what we have on the left hand side? Well, on the left hand side we have modulus of x, and because x is a non-negative number, it will come out as x. And what about the right hand side? Well, right hand side has modulus of y, and in this case y is also a non-negative number, so it will come out as y. So then from here, can we say that x is equal to y? Now let's go for the second case. So for the second case, let's take both of them as negative. So let's say x is also negative and y is also negative. So then what would be the left hand side? Well, left hand side has modulus of x, and that would give us negative x because x is a negative number here. Similarly, what we have on the right hand side? Right hand side has modulus of y, and y is also a negative number in this case, so this will give us a negative y. And from here, because modulus of x is equal to modulus of y, we can say, well, then negative x is equal to negative y. And from here we can say, well, if we multiply both sides by negative 1, so that will give us x is equal to y. So let me highlight them. So far we are seeing that x is equal to y. Right? We have 2 more cases to consider. So let's now go for the third case. Here let's take x as non-negative and y as negative. So then what do we have on the left hand side? Well, left hand side has modulus of x, and because x is non-negative it will come out as x. And how about the right hand side? Right hand side has modulus of y, and because y is negative it will come out as negative y. So from here we can say, well, in this case x will be equal to negative y. So that is another observation. Let's highlight that. So in the first two cases, as you can clearly see that in the first two cases we saw that, well, if modulus of x is equal to modulus of y, then x is equal to y. In the first two cases we could see that x would be equal to y. Now in the third case we are seeing that x can also be equal to negative y, right? So now let's take the fourth case. In the fourth case we are going to take x as negative and y as non-negative. So here what would be the left hand side? Left hand side has modulus of x, and because x is negative it will come out as negative x, and right hand side has modulus of y, and because y is non-negative it will come out as y, and because the original condition says that modulus of x is equal to modulus of y, so here our observation is that negative x is equal to y, and if we multiply both sides by a negative 1, then left hand side will become positive x and the right hand side will become negative y. So clearly you can see that in the fourth case also we are getting this possibility that yes, x can also be negative y. So here are the other two cases where we see that x can also be negative y. So if we combine all four cases here, we can say, well, then x can be positive y or x can be negative y, and that's exactly what we needed to prove, that when modulus of x is equal to modulus of y, then x will be equal to either positive y or negative y. So both possibilities are there. Next, let's talk about a similar looking property, and the property is like this. So let's see how we can prove it. Well, before we go too far, let's understand one thing real quick, that in this case a must be a non-negative number. Why? Because modulus of any real number, in this case modulus of x, is supposed to give us a positive value. So that means a must be a non-negative number. A could be 0 when x would be equal to 0, or a has to be some other positive number, right? So a cannot be negative, and if a is negative, so let me make a quick note here that if a is negative, that would mean that this equation has no solution, because modulus of any real number always gives us a positive value. And if we say, for example, if somebody says, hey, can you solve this? You can easily say that this has no solution, because modulus of any real number can never be a negative number. It always has to be either 0 or positive. So this has no solution. That's exactly what I'm trying to say here, right? If a is a negative number, then obviously this equation has no solution. Now, if a is not negative, then yes, then it has solution. And how to prove that? Let's see. So we can take the two other cases when a is equal to 0. If a is equal to 0, we can clearly say that modulus of a real number is equal to 0. That means that real number also must be equal to 0. So that is a solution there, right? Which is again equal to a, because a is 0 in this case. So if a is 0, the modulus of x is 0. That means x is equal to 0. And again, the 0 is equal to a. So that is why I'm writing it like this. So from here, you can clearly see that, well, here we are proving that x is equal to a. And let's take the other case where a is a positive number. So if a is a positive number, from here what can we say? There are two possibilities. X can be a negative number or x can be a positive number. So when a is positive, then I'm taking two cases right here. So under a is positive, let's take two cases. Let's say we have case 1, x is non-negative. Then what will happen? Modulus of x, which is the left hand side. So left hand side can be written as, as x, because x is non-negative, so it will come out as positive x. And then how is our original equation going to look like? Well, from here we can say, well, then looks like x is going to be equal to a. And then let's take the second case. In the second case, let's take x as a negative number, and then what would be our left hand side? Because x is a negative number here, it will come out as negative x. So from here, the original equation that says that modulus of x is equal to a, so we can write that in this case it would be negative x equal to a, and from here if you multiply both sides by a negative 1, so it will become positive x equals negative a. So far we are seeing three solutions here, actually two distinct solutions here, because x equals a and x equals a right here. You see this one right here and this one right here, they're actually only one solution, x equals a, and here we have another solution which says x equals negative a. So from here can we conclude that yes, finally we can say that x will be equal to positive a or negative a. So from all of these we can say okay, therefore x will be either a positive a or a negative a, and that's exactly what we wanted to prove. So the property says that modulus of x equals a would mean that x is equal to plus or minus a, and that we have proved already, right? Okay, let's move on to the next property. The next property says that modulus of x being less than or equal to a would imply that x will be greater than or equal to negative a and less than or equal to a. And this is a very important property that we often use in solving modulus inequalities like this. So now let's see how we can prove it. Well, first of all, let's see what are the different values of a are possible here, right? So can we have a less than 0? Can we have a as a negative number there? Well, if a is a negative number there, then this equation has no solution, because a modulus function can never be negative. And if we ever say, hey, modulus of x is less than or equal to say negative 5, that has no solution, because it can never be a negative number. Modulus of any real number can never be a negative number, right? So when a is a negative number, it has no solution. So I'm going to say in this case there is no solution. And then what about a equals 0? If a is equal to 0, then here we can say, well, then x will also be equal to 0, and that's for the equality. That is when the equality holds, that modulus of x will be equal to a when a is equal to 0, and in that case x also must be equal to 0. So I can say equality holds right here. When a is equal to 0, for this value we can say equality holds. And then the only other situation is a greater than 0. So when a greater than 0, that means a is a positive number. Then let's see what happens to our left hand side. Well, when a is a positive number, our left hand side can have two different cases. Case 1, let's take x as a non-negative number. If x is a non-negative number, then our left hand side, which is modulus of x, that is going to be exactly like x. So then from the original inequality, can we say that, well, then in this case x will be less than or equal to a? That's from the original inequality that's been given there. Alright, now let's take the second case. In the second case, let's take x as a negative number. If x happens to be a negative number, then what would be the left hand side here? Well, the left hand side has modulus of x, and that will be equal to negative x, because x is a negative number, so he will come out as negative x. So then from the original inequality we can say that, well, in this case looks like negative x is going to be less than or equal to a, and if you multiply both sides by a negative 1, then we can say x is going to be greater than or equal to negative a. We are multiplying both sides by negative 1, so the inequality sign will flip. So here we see that x will be greater than or equal to negative a. And then if we combine these two observations or these two results, that x can be less than or equal to a or x can be greater than or equal to negative a, so the combined picture going to look like this. I'm writing it here in red, so we can say x is going to be less than or equal to a and greater than or equal to negative a, and that's exactly what we wanted to prove. For example, if somebody says modulus of x is less than or equal to 2, then from here we can say, well, using this property we can say, well, then x must be greater than or equal to negative 2 and less than or equal to 2. And if we have, let's say, another example, suppose if somebody says that modulus of x minus 5 is less than or equal to, let's say, 10. So from here what can we say? Well, from here we can say that whatever we have within the modulus sign, that quantity which is x minus 5, that quantity will be greater than or equal to negative a, which is in this case 10, and less than or equal to a, which is 10 again. And if you simplify that a little bit, now if you add a positive 5 in all three portions of this compound inequality, then we can have negative 10 plus 5, that would be negative 5, and then here it will be x minus 5 plus 5, that would be x, and then here again it will be 10 plus 5, that would be 15. So this will be the situation here. So the solution here would be x will be greater than or equal to negative 5 and less than or equal to 15. And you can validate that. You can take some number, right, between this range. Let's say suppose we take a number 1, right? If we take 1 as the value of x and if we put that in the original inequality, you see that x minus 5 when x is equal to 1 will evaluate to negative 4 right there within the modulus sign. So when it comes out, it will become 4, and obviously 4 is less than 10. And if we take 15, for example, suppose let's take this one of the extreme values. So suppose we take x equals 15, and let's try that in the original inequality. So if x is 15, then it would be modulus of 15 minus 5, that would be modulus of 10, and that will be equal to 10. So the equality also holds true. Now let's talk about the final property here, which I planned for this video, and that is going to be like this. This property says that if modulus of x is greater than or equal to a, that would mean that the solution here would be x is greater than or equal to a, or x is less than or equal to negative a. And we should be able to prove it in a similar way. So now let's take the different possible values of a. So first we are going to take a as a negative number. So here is our first situation when a is negative. And if you think about it, when a is negative, that means we are probably talking about an example like this. Say suppose I have an example, say suppose modulus of x is greater than or equal to negative 5, for example. And if you think about it, the equality will never hold true. However, the modulus value of any real number will be a positive number, and that will always be greater than negative 5. So then this inequality will be true, because whether it's equal or not does not matter. At least one part of the inequality is true. That means modulus of x will always be greater than negative 5. So when a is a negative number, the solution is that it is true for any value of x. So I'm going to write it here. It is always true. So the original condition will be always true. When a is a negative number, modulus of x will always be greater than or equal to a. That will always be true. Let me write it like this. When a is less than 0, then modulus of x greater than or equal to a, that would always be true. It will always be true. And if it is always true, that means it is true for any values of x, right? So that means x will be any real number. And if you use the interval notation, you can say, well, in this case, we can say that x will be from negative infinity to positive infinity. It can take any value in this range. And that essentially means x can have any real number. For any real number x, this inequality will always be true if a is a negative number. This is very important. You need to understand this clearly, that if a modulus is written like this, that greater than or equal to negative 5, then you can assume that it is true for any real value of x. You can try any real value of x, you will see that this is coming out to be true. Now let's take a equals 0. Well, when a equals 0, modulus of x definitely must be equal to 0. This would imply that it is possible only when x is equal to 0. So the solution here is that if modulus of x is equal to 0, then x is equal to 0. And now if a is a positive number, let's see what happens. Well, when a is a positive number, now we have two possibilities. We are going to take two cases. Let's assume that x is non-negative. Then what is the left hand side here? Well, left hand side has modulus of x, so we can say left hand side will be x, because in this case x is non-negative, it will come out as positive x. So then based on the original inequality, we can say, well, then x will be greater than or equal to a, because the original inequality says that modulus of x is greater than or equal to a. So from here we can say, well, then modulus of x must be greater than or equal to a. So from here I am writing that x must be greater than or equal to a, because modulus of a is actually x right here. So we can say x must be greater than or equal to a. That's one observation. Now let's talk about the other case. When x is a negative number, what would be the left hand side in this case? It will come out as negative of x. And here again, from the original inequality, we can say, well, then in this case it will be negative of x greater than or equal to a, and if you multiply both sides by a negative 1, then it will be positive x, and the inequality sign will flip and it will be negative a like this. So that is another observation. So those are the two possible solutions here. that when a is a positive number, then we have two possible solutions. When a is 0, x will be 0. When a is a negative number, x can be anything, any real number. So now if you look at all three cases here, right? If you look at all three cases here, that one possibility is right here. When a is a negative number, then x can be any real number. The second possibility is when a is 0, x can be 0. And then from the third possibility, we have two possible solutions here, that x can be either greater than or equal to a or less than or equal to negative a. And we can show this graphically also. So let's try to do a little graphical representation here. So here I have a graph of modulus of x. So here y is equal to modulus of x. So this is a graph of y equals mod of x. And if somebody says, hey, mod of x must be greater than or equal to, let's say 2 maybe, right? Let's take a number. Say suppose this is our 1 and this is 2 and then 3 and etc. Right? In this inside negative 1, negative 2, negative 3, etc. So if somebody says that modulus of x must be greater than or equal to 2, so you can see that we can take the point 2 on the graph, which would be kind of like here. So this is, let's assume that this is the point 2, and here on this side also we'll have almost at the similar location there will be point 2 right there. So if somebody says that modulus of x, so in this graph it will be the value of y greater than or equal to 2, then you can clearly see that the solution would be the value of x must be beyond this point, meaning starting from here, any values of x greater than 2 will give us a value of y which will be greater than or equal to 2 right here. So starting from 2, any values of x will give us a value of mod x which will be greater than or equal to 2. And similarly on the left hand side also, if you see that if we, this is our negative 2, so let's say this is our 2 right here and this is our negative 2 right here. And then again, if the value of y, which is modulus of x, has to be greater than or equal to 2, then it would be like this portion of the graph, the yellow portion of the graph. I am trying to draw it right here, and that yellow portion of the graph will give us a value of the modulus greater than or equal to 2, and that is possible for which values of x? If you think about the negative x-axis here, you see that this part of the negative x-axis, any values of x will give us a value of y which will be greater than or equal to 2. So that is why if you see this portion right here, x is greater than or equal to 2 in this yellow zone right here on the positive x-axis side, and on the negative x-axis side this is actually x is actually less than or equal to negative 2. And those are the two possible solutions that we discussed already so far. So this is one possible solution and this is another possible solution. So graphically also we can clearly see that only for those two solutions we will get the value of modulus of x greater than or equal to a particular number. In this example I took 2. I took a as 2 in this particular example, and it can be any positive number, right? So this is how we have those two solutions, and you can apply the same concept in the previous property. So let's scroll up there and let's see how we can graphically show that this is also true for the situation where we say modulus of x must be less than or equal to a. So here again let me draw the graph real quick. So here again, if somebody says, hey, modulus of x is less than or equal to, let's say 3. So in this case I am taking a as positive 3 right here, right? So the point would be on the graph, the point would be somewhere around here, and similarly on this side also it will be somewhere around there. So those are the 2 points on the graph of the modulus function, which is equal to 3. The value of y is 3, so that coordinate of those points would be 3, 3. And if somebody says that this value has to be less than or equal to 3, then which zone it would be? Well, then it would be this zone right here. Clearly this yellow zone will be the value of y, which will be less than or equal to 3, this yellow zone right here. And within the yellow zone, what is the value of x? Again, I am doing another yellow zone on the positive and negative x-axis. So this will be the value of x, for which the value of y will be less than or equal to 3. And here you see that x is from negative 3. So if this is our negative 3 right here, this point right here, and then if this is our positive 3, then you can clearly see that x has to be greater than or equal to negative 3. So now I am writing in yellow right here. So x has to be greater than or equal to negative 3 and less than or equal to 3 to satisfy the condition that y will be less than or equal to 3. In this example, I took a as 3. So on the graph, you can clearly see that the value of y will be less than or equal to 3 when x is in that yellow range on the x-axis. So you can clearly see that graphically also that yes, this result is actually true. That if somebody says modulus of x is less than or equal to a when a is a positive number, then you can quickly write down the solution that, well, x must be greater than or equal to negative 3 or negative a and less than or equal to positive a. I hope everything made sense. There are some more inequalities of modulus function that I will be discussing in the subsequent videos. But for this second part of the video, we are pretty much done. Thank you for watching. See you in the next video.